right, section 9.4, we're going to be taking a look at permutations and combinations. And part of what this sort of harkens to, and we talk about this in contemporary math, if you've had contemporary math here at OBU, is counting techniques. How do we count things up? Now, it's going to go a little further than that because of the way the discussion is geared here, but that's what we're looking at. And to begin with, we have to have a little bit of notation that you may or may not have seen before. It looks like an exclamation point, okay? So we have this n, and it looks like an exclamation point, and then I've got another one up here that says 0 and an exclamation point. So definitions, what these are, n factorial is actually the number n multiplied by one less than that value and another number less than that value, and you keep going until you get down to the number 1. So if this said 8 factorial, you do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Make sense? So you're just multiplying it by everything less than that, all whole numbers. This is what it's working with, all whole numbers. And then 0 factorial needs a definition. You'll see why when we get to the formulas that we're using. But 0 factorial is defined. Its definition is that it's equal to 1. Right? It's not a provable fact kind of thing like our exponent rules where we said, oh, look, a to the 0 is always equal to 1. There's a way to prove that. That's actually a true statement. We don't have to take that for granted. Here we have to take it as a given. It's a fact that we're going to go with as a given. All right, there is a fundamental principle of counting that's found in chapter 2 of your book. If you've had number theory, you've seen it before. If you haven't, it's not a problem. But that's where this is actually showing up. I'm sorry, I skipped one. Let's do 4 factorial first, and then I'll talk about that. So 4 factorial means that I need to do 4 times 3 times 2 times 1. Just multiply 4 down to 1, right? 4, 3, 2, 1. And when we multiply these, what do we get? It's 24. Okay, so that's factorials, in action right there. All right, sorry. Stop for a minute there and go back to what I was saying now. Our fundamental counting principle says the following. If we have 2 events, m and n, and we want to know how many ways those 2 events can happen sort of in sequence, then if m can happen in little m ways and n can happen in little n ways, then the number of ways those 2 things can happen in order is m times n. And it's expandable, right? It doesn't just have to be 2 events. You can do it for 3 events or 4 events or however many events you want. You just multiply their outcomes together. So we're going to do Pizza Planet. What's Pizza Planet from? Toy Story. Very good. Toy Story. So we may not know about the lottery, but we know about Toy Story. It's all good. Toy Story. Pizza Planet offers 3 kinds of salads, 15 kinds of pizza, and 4 desserts. Assume there's like a meal deal, and a meal deal consists of a salad, a pizza, and a dessert. And we want to know how many different meal deals there are. Well, there's 3 different things that we have as events. We have the salad, we have the pizza, and we have the dessert. And we multiply the number of salads, that's 3, times the number of pizzas, that's 15, times our number of desserts, that's 4, and that will be the total number of meal deals. That's the fundamental principle of counting in play. And what do you get if you multiply these out together? It is 180. So there's 180 different meals of this variety. Okay, so we're going to be using this as one of our counting strategies. There's going to be some others. The next counting strategy is something called a permutation. So there's 2 different types of permutations. The first one we're looking at is a permutation of like objects. So let's think about that as what it is in just a second, but let's just write the definition pieces down. We have n elements, r1 of which are alike, r2 are also alike, all the way up to rn. Alike objects, that's terrible English, I know, but pretend in a minute. Objects that are alike, would be better, are indistinguishable. Then if we want to know the permutation, how many permutations there are of these objects, it is n factorial divided by each of those different indistinguishable objects and their factorial. So we have r1 factorial, r2 factorial, all multiplied out times n factorial. And I think the easiest way to justify or to describe what's happening, and I'll give you some other examples after we do it, is to show the example that I have next. Are we good with that? Because it involves candy. Candy is always good to talk about. Starburst is a really good one. You can use anything that's indistinguishable. So you can think Skittles is a really good one we could do. You could do Smarties. You could do M&Ms. It's a package of something with objects that have repeated colors is usually how you think of it in terms of this candy argument. And I'll give you some other arguments too, but candy is a really good, easy one, this one. So in a package of Starburst, this package has 4 red, 5 pink, 3 yellow, 2 orange. That's a pretty good package, in my opinion, because the yellow and orange I don't care about. Actually, I only care about the pink, to be honest, but that's okay. So we got lots of pinks and reds. The question is, in how many different ways can you eat the Starburst? Okay, so if you eat pink 1 or you eat pink 3, you're eating pink. Those are indistinguishable choices among pinks. Do you understand? So that's what it means when it talks about things being alike. All the pinks are alike. It is impossible to distinguish which pink you ate from another pink because they're all the same. Okay? So when we're counting these objects, what we're doing is we're figuring out first how many Starburst, in this case Starburst, do we have? 14. We have 14. That's the value that's going to go on top. There are 14 different pieces of candy that we're going to eat, assuming we ate the whole package, right? But some of them are indistinguishable from one another, right? Like all the pinks are indistinguishable, and there's 4 of them. So I'm going to have a 4 factorial in the denominator. All the reds are indistinguishable, and there's 5 of those. So I have a 5 factorial in the denominator. We have yellows. All the yellows are indistinguishable. There's 3 of those. And we have our oranges, and the orange are 2. And if we have counted and taken into account everything that's there, the denominator, if you just add the values of the numbers together, should be the same as the 14 on top, which I believe it is. Does that work? Okay. So you have a couple of options. This one's small enough that you might actually be able to multiply 14 times 13 times 12 times 11 all the way down to 1. You might be able to do that. Depending on what number is in the numerator, though, you might not be able to. It might get to the point where your calculator can't handle the number. It's so large, and it will truncate it, which means it'll shorten it, and it'll put it in scientific notation. That means it's approximating it, and that's not helpful. Okay? So I'm going to assume that that could be happening on the top to show you what would happen if you can't multiply it out. Everybody good? So what we're going to do is we're going to write down what this is. So this is 14 times 13 times 12, and I'm going to write the whole thing out till times 1, just for this one. And then we'll talk about how we can abbreviate it next time. And I'm not only going to do that on the top, I'm going to do it on the bottom as well. So 4, 3, 2, 1. 5, 4, 3, 2, 1. 3, 2, 1, and 2, 1. Okay, I don't know about you. I know about you, actually, too. You don't want to really write this all out every time, right? We would prefer not to write this out every time. It gets looking really messy. Minimum, at minimum, you could leave out the times 1s. True? They don't add any value to what we're discussing. So if you just left out the times 1s on the bottom and on the top, that would be helpful. But there's a bit more helpful things that we can do. For example, notice this one at the end, 5, 4, 3, 2, 1, matches exactly this one right here. Do you see that? So if I have times 5 times 4 times 3 times 2 times 1 in the numerator, and I have times 5 times 4 times 3 times 2 times 1 in the denominator, that's reducing a fraction. I don't need those there. They reduce, they cancel out. Okay, I'll show you another way to write this later that avoids writing them out to begin with, but for the moment, that's all right. At this point, again, you're welcome to just multiply the numerator together, multiply the pieces that are left in the denominator, and see how many you get. You're going to get a whole number every time you do this, and that's fine. You can do that. But you could also take a look at ways that you can cancel some other pieces if you wish. For example, 3 times 2 here. That's the same as 6. I can cancel those. Or do you see any others that you could cancel by like pairing them up or something like that? 4 times 3 is 12. Fantastic. There's not much left in the denominator, just 2s and 1s. I do not have a 4 still in the numerator, but this 2 and this 2, which make 4, could reduce with something on top. They could reduce with the 8. So if you wanted to do that, you could as well. So you could mark this 8 out and make it a 2, up here. The one thing to be really careful about as you're doing this is that when you get to the point where you multiply it, that you don't accidentally forget one of the pieces that you're supposed to be multiplying. So just take care as you're putting this into the calculator that you get everything there and you don't get any extras. So you have 14 and 13, 11 and 10, 9, 2, and 7. This is a big number. So somebody tell me what you get when you get to the point of multiplying them. I think that's right. Yes, indeed. So there's 2.5 million ways to eat that package of Starburst.
22,520.
Oh, I just misheard you. And 22 is what I have there as well. Perfect. Lots of 5s and 2s. And then there's that little lonesome 0. Let me show you a shorthand way that means that you don't have to write all this out to start with. Sounds good? Okay. So what you could do instead is that you could write the 14 out, but you can just stop when you get to the biggest denominator, 5. So I can write 14 times 13, good grief, times 12, 11, 10, 9, 8, 7, 6, and 5 factorial. That matches with the 5 factorial on bottom. The rest of it you don't get for free, though. You have to write those pieces out. So 4, 3, 2, if you don't want to write the times ones, that's fine. Then you're going to have a 3 and a 2, and you're going to have a 2. So leave off the ones if you wish, but the 5 factorials will cancel. So you can't reduce factorials. Like if you had 10 factorial on top and 5 factorial on bottom, you can't cancel the 10 and the 5, okay? You can only cancel them out if they're exactly the same. And the reason is because that means their expansion is exactly the same. 5, 4, 3, 2, 1, 5, 4, 3, 2, 1. And then from here, we would just do the same sort of cancellations we had done before. Does that make sense? Okay, I think we're going to stop there because the next two, grouping them together on the same day makes the most sense. So we're going to push pause right there and pick this up on Monday.